Welcome to this overview of Rocket Science 101, which is my introduction to launch vehicles and orbits. This course is a standalone introduction to launch vehicles, orbits, and encourages an approach for conducting and documenting research, a good skill for any student. In the introduction, I have a film clip that is a very good historical statement of how we got into the space program and the Apollo 11 moon landing. I end the introduction with the growth in global interest in launch vehicles and their satellite capabilities. In Chapter 1, I present a system-level introduction to launch vehicles and their initial or parking orbits. Chapter 2 then decomposes a typical launch vehicle into its system elements or subsystems. In Chapter 3, it provides an introduction to performance of selected launch vehicle families, both old and new, that the student might use for further study. The Chapter 4 is an explanation of a launch vehicle design approach and explain how it would normally start with a concept definition phase in the commercial arena. Finally, in Chapter 5, it identifies Earth orbits and their uses and the impact of using the East and West Coast launches in the United States. Each chapter is rich in maps, diagrams, tables, photographs, and online video references to provide a multimedia approach and help keep it interesting. You typically will start with a simple introduction or explanation and then add complexity. If the student wants to learn more and dig deeper into rocket science, there are some more advanced references to using the Rocket, Orbit, and Missile Analysis System called ROMAS, which can be found at rocketscienceprograms.com. This course material, however, is provided completely free of charge. Contact me at developer.romas@gmail.com if you are interested. So the purpose of this course serves two. First, be a standalone introduction to rocket science and also help understand the science behind ROMAS programs. Chapter 1 has 5 major topics, as you can see on the chart. It starts with a brief introduction of the two systems of units that the student will find as they are doing research. Next, you'll find an explanation of the forces on a rocket during launch and the ascent trajectory, going from launch to the initial parking orbit and possibly transfers to the final orbit. Then there's a deeper dive into the Earth-related forces that impact rocket velocity, some negatively, for example, gravity, drag, engine back pressure caused by the Earth's atmosphere, and some positive, that is, launch location, which is usually helpful and advantageous if you launch from the East Coast, but maybe less useful or less helpful and sometimes even negative for West Coast launches. Finally, there's a preliminary introduction to the treatment of orbits from U.S. launch locations until there's a more detailed treatment of orbits in Chapter 5. Chapter 2 identifies the key elements or subsystems that are common to launch vehicles. Starts off with considerations that are used to determine the number of stages that are desired for a new vehicle, and then goes into the key elements or subsystems, including the fairing or nose cone that protects the satellite while it's still in the Earth's atmosphere, the satellite or payload itself, key structural members including tankage for the propellant, payload adapters, inner stages, skirts, and so on. Then hits on liquid stages and their engines with their advantages and disadvantages, and then solid stages, again with advantages and disadvantages. The chapter ends up with the key equations that may be helpful in gathering data when you have some information but are missing others, such in the area of thrust and specific impulse. Chapter 3 identifies sets of launch vehicles, launch vehicle families, both new and old, that the student might find interesting. They list the launch vehicles and various engines on a wide range of performance to allow selection of launch vehicles for further study. The 8 families that I identify fall into different categories. The NASA vehicles, for example, have the most detailed information that's required for detailed study. I have stuck to primarily US vehicles because of the commonality of launch impact from launch location, and that's primarily Cape Canaveral or Kennedy. The Ariane is the exception, as it shows the advantage of being launched near the equator and provides the easiest access to geostationary orbits because of the minimal plane change and high pickup of velocity from the Earth rotation. Limited work has been done on solid rocket motors and stages with solid rocket motors due to the lack of detailed solid rocket motor information that is available from the manufacturers. The whole purpose of Chapter 3 is to get the student interested in real-world vehicles, to do some research, and to use them as models for their work. Chapter 4 represents the most complex and technically challenging topic in this course. To help understand this process, I've started off with a brief introduction to the Air Force Academy's systems engineering process. As you can see, this process starts off with the conceptual design phase. Early in the CD phase, there are explorations of many different concepts where quick and dirty tools are needed to define and explore these concepts and their decision space. Here the term dirty means the use of tools that provide only rough order of magnitude or ROM accuracy. Within this approach, I've developed 3 levels for designing or modeling of vehicles. Level 1 is the easiest, minimal data collection. However, the data is usually less accurate, more error prone. Level 2 is more difficult, but gathers a small amount of data, but very accurate data from NASA flight reports. Level 3 requires lots of NASA data to be gathered, as it is more required and very accurate data is needed to build an extremely accurate launch vehicle performance. The earliest data to gather I call wiki data because most of it comes from wiki sources. The most accurate data I will call NASA data, and it can be found in specific flight-related reports. Either data can be used to model or create a new design, just the NASA data is better and more comprehensive than the wiki data. Chapter 5 explains the basics of Earth-centered orbits. It starts off with a description of the 6 Keplerian classic orbit elements, or COEs, and those are needed to describe an orbit and a satellite's position in that orbit. Next, there's a top-level explanation of the key orbit types, and then a deeper dive into the 6 general commonly used orbits that are listed above. Topics such as apogee and perigee altitudes, inclinations, and orbital periods are covered. The limits placed on launch vehicles from east and west coast launch locations and the typical resulting ground tracks are also discussed. Finally, the growing problem of space debris is introduced. This chart shows the wide range of key references that have been used in the development of the course. And as you can see, everything from textbooks to specific flight reports, other guides of information, Wikipedia, and at least 70 YouTube videos provide, hopefully, an interesting approach to this topic. To conclude with one of my favorite rocket science cartoons from the far side, I hope this course will inspire students to want to learn more about rocket science. Thank you.